So when we talked about how the electric potential energy of a charge moving around an electric field changes, we focused on two special electric fields. The first of those was a constant electric field. And so let's come back and think about that same type of field, but now think about how the electric potential changes. When we think about moving within a constant electric field, the first really fundamental question that we need to ask, and we talked about it in the previous video, but it's worth coming back and talking about again, is what is it that's moving? When we talked about the electric potential energy, it was clear that we had a charge. You started with a charge here, you moved it there. So for the change in electric potential energy, a charge was being moved from one point in space to another. But when we talk about the electric potential, we're not moving a charge. We, as the observer, are moving from one point in space to another. So this is one of, again, the subtle things that we need to become comfortable with, is in the same way that we talked about with the electric field, unlike the electric force, it was just talking about a point in space. There wasn't a charge there. The same thing's true in thinking about the electric potential. I don't have a charge that I'm moving around. I'm simply starting at one point in space, and I'm moving as the observer to a second point in space to figure out what's going on within that electric field. So when we talk about moving within an electric field, it's us that's moving, not a charge. Well, we can start with the equation that we had for calculating the change in the electric potential energy of a charge as it moved around, and we said, well, that was negative Q E times delta X. Well, if the difference between the change in the electric potential energy and the change in the electric potential is just dividing out the test charge, getting rid of Q gives me what the equation is for thinking about how the electric potential is changing as I move within my constant electric field. So what I get is negative E magnitude of the electric field times delta X. Delta X is still the displacement parallel to the electric field, so it doesn't care how much I move perpendicular to the electric field. And just like before, delta X is positive when we move in the direction of the electric field. Delta X is negative when we move opposite the direction of the electric field. What this means, of course, is that you decrease the electric potential moving with the electric field. If E is always positive, if you make delta X positive, that negative sign says you're going to get a decrease in the electric potential moving with the field. If you make delta X negative, the negatives will cancel and you get an increase in the electric potential moving with the electric field. Like we did before, knowing whether or not we're moving with or against the electric field means instead of burying a sign in here and keeping track of whether it cancels or not there, why don't we just take care of the sign out front? So what we're going to choose to do is write the change in the electric potential in a constant electric field by using this equation, magnitude of the electric field times, again, this distance, always positive distance that we're moving parallel to the electric field, and then I'll use a plus sign if I'm moving opposite the direction of the electric field, minus sign if I'm moving in the direction of the electric field. I need a positive when I move against the field, negative when I move with it. This delta D parallel, just like was true with the electric potential energy calculation, it's just a positive distance, and again, it only cares about how you're moving with the electric field. So if we change where our second point is, so we start here, and instead of moving just straight along the field to the right, we move to the right and down. Again, notice the and down part I don't care about, so I still have that same delta D parallel distance that tells me how much I moved with the electric field in this situation. So what that means is there's an entire set of points that lie along this line where I'm moving perpendicular to the electric field that will all have the same potential. So it doesn't matter whether my second point is here or down here or up here, as long as it lies along this line, because that parallel distance between my initial point and any point along this line is the same. The potential is the same at at every point along the line, which means that this is an equipotential line. So because moving perpendicular to the electric field means you don't change the electric potential, moving perpendicular to the electric field gives you an equipotential line. Just like with the electric potential energy, we can talk about the electric potential, but that of course still means the electric potential relative to the point where the electric potential equals zero. And in our constant electric field, we get to choose. So I can pick a point where the electric potential equals zero. In this case, again, I'll just put it right here in the middle. And then if I want to talk about the electric potential at some other point in that field, I need to take care of a plus or minus magnitude of the electric field times what's this distance that I'm moving parallel to the electric field to go from the zero line to wherever my new point in space is. And again, we can frame this like we did gravitationally with above or below, but the nice thing here is this is pretty easy. We need the plus sign when we move against the electric field. So here, moving from the 0 point to where this point P initially is placed, I can see where my d parallel distance is, because I only care about the distance parallel to the electric field, and above means this one will be positive because I moved against the field. So here, above, using a positive simply means if you went against the electric field, we're going to use a positive. If I put P over on the other side, well, I had to move with the electric field to go from my 0 line to this new point P. So it still has the same d parallel because it's the same distance away from that 0 point. Because I went with the electric field, I need a negative in terms of calculating its potential relative to the 0 point. So this one's pretty easy. Above is simply another way of saying you moved against the field, below with the field. So we'll use pluses when we move to points that required us to go against the field in getting there from the 0 point. We'll use a minus when we go to points where we moved with the field from the 0 point.